Hey guys, welcome back to another episode. Today we're going to continue what we were working on yesterday, finishing up our Octree color quantization visualization, and then after that, what are we going to do? We're going to start working on the OpenGL stuff one more time. I have a bit of pseudocode I wrote that should work for that triangle of triangles nonsense that I had a whole bunch of trouble on before. Let me see if I can just find the code real quick, and there it is. So everything should be good to go. And of course, if you guys have any questions or anything like that, let me know as I'm going through. Let's start by talking about what color quantization is and what exactly we can do with it. Also, let me get some water since I'm thirsty. But yeah, so we've got a lot of stuff to do. Okay, good. So, let's go ahead and pull this out. Let's get started. So, all the simulations we're running right now are all related to something known as an octree. An octree is basically a method to represent particles in space. Here's the idea. We have a big box. Pretend I can draw. In this box, we have a whole bunch of particles. Hey, Watakanai, what's up? How are you? I am fantastic. Thanks for asking. Okay, so we draw. Basically, what we do is we continually subdivide the space again and again and again until every particle has its own box. Once that happens, we have something known, in this case, in 2 dimensions as a quadtree, but if it were in 3 dimensions, it would be known as an octree. And by doing this, we have a way to represent every single particle based on a tree, instead of based on free space or an array. This allows us to go through the tree much faster than we would be able to do free space or anything like that. So, for example, if we're doing, let's say, force integration, we can just check this particle. Let's see, this particle against this entire box over here and save basically 3 checks, right? Because now we aren't checking 1, 2, 3, we're just checking against this entire box. And that's quite useful, right? The application we're working with now, hey I care, is instead of free space, we're working with red, green, and blue. So you could imagine we have red going this way, green going this way, and blue going maybe somewhere off the board, like this. And the idea is that we can treat all particles that are within, let's say this box here, all as the same color, let's say blue, which is the center of mass of the big box. So this allows us to basically take all of the colors in our image and lower the quality. And I know we had a couple questions yesterday on why we would want to lower the quality, and it's simply for compressive purposes, right? So the idea is that we are reducing the number of colors, making it easier to store that image. And sure, there might be other reasons too. I just personally find it a cool algorithm, and I kind of wanted to highlight it just because I thought it was, well, interesting to me. So, sorry about that. There's a lot of details here and there. And we've kind of been through all those details before. In fact, we do have the color quantization working. So, if you have any questions on how this works, that is fine. Let me see. It's fine. By the way, I benefit a lot from when you work with eigenvalues and vectors when it came up in linear algebra class. I'm glad. I find that a lot of people enjoyed that particular video a good bit, simply because it, I think, had a pretty good visualization of what exactly an eigenvector is. And I'll be honest, it took me actually a few years before I actually understood what an eigenvector was. Like, it's used all the time in physics. But I was introduced to it, and I just knew it as a mathematical concept. I didn't think it had any physical representation until, I looked into it. And so it's one of those things that I just don't think is taught very well. One thing I want to point out, though, is about my YouTube channel and videos and stuff like that. Every once in a while, I want to do, like, an educational video, but I like doing simulations, too. And so I haven't quite decided the proper balance for that. I think what I'm going to do is create a new video for when I hit 1024 subscribers, which is going to be a vlog video. And in that video, I'm going to just talk about where I want to go with the channel and stuff like that. And we'll see what people think about that. You know, I kind of want people's opinions and things. I mean, 1,000 subscribers isn't like that many, but it's a lot for me, and I'm quite happy with that. Let me think. Yeah, so I'm glad it helped, and let's go ahead and get started with the color quantization stuff. First, by showing you what the code actually does, and then by actually doing the visualization, which I think will turn out quite well. We're pretty much done with the visualization as is, just a little bit of stuff here and there. I'm expecting it to take maybe 30 minutes to get done with this visualization and go from there. Hey, Gusrun, I noticed that Happy Little Rat was streaming, so I I don't know if he's done or not, but I hope that went well. So let me go ahead and do, let me see, what do I want? I want to CD into projects, semi-layouts, and of course, color quantization, and press enter. And CD projects, semi-layouts, and color quantization, and there we are there. So let me just go ahead and do an ls here, and let's do mirage out.bmp. Okay, we have like nothing here. It's just one very quick image. Okay, I didn't know he just started. That's fine. Okay, so let me go ahead and do an ls here. We have all these images that we were working with. One thing I want to point out is what we did yesterday. So if I run blender-p color quantization.py, give it just a second to run. I'll go ahead and move the Blender screen up here and down here. Okay, you'll note that we have a box. Now, if we move this box out of the way, we have a whole bunch of smaller boxes in there. Okay, so what I want to do is I want to basically show you what we see when we render it. And you'll see that, oh look, we have our octree, and that's great. We have almost exactly what we want to see. I apologize, the rendered view maybe isn't the easiest one to understand what's going on, because every time I move it, we see the whole thing re-render. But it's pretty useful. Relaxaman, I am from the United States. I'm currently living in Okinawa, Japan. Okay, so let me think here. Basically, we have the octree being visualized, which is great. That's what we want to see. Now, what else do we have to do? Well, we have to make so each of these boxes appears at some particular point. So right now, let me see. I don't think anything's happening with time. So we have to make it so something does happen with time. And that's basically where we're at right now. It's kind of neat, this rendered view. Anyway, let's go ahead and close this. And let's open up color quantization.py. Now let's go down to the very bottom. And what do we have here? We visualize octree, and we also have, let me see, where are we? Define scene. There should be, let me see, there should be like a cage set or something like that. Sorry about that. Okay, here we are. So, what we're doing here is we are essentially going through and placing all the frames down, right? So we start at frame 10, we do our cage set, and then from there, we basically want to add a new box every 10 frames. That's what I've said here. Or add 8 new boxes every 10 frames. That's what I was going for. However, if I go down to the create frame function, which should be cage set function here. Hey, Digita. Then what do we have here? We are putting in box length, XYZ, and make frame. However, this is all for cube 001, which is not the frame that we currently have. So let's go ahead and go through and fix this up. All we have to do is read in an additional ID here, and then put that ID into all of these guys here. So first, let's go ahead and create the ID for each of these boxes. So let's go up here. Just so I don't forget, where are we? Oh, let me just press N. There's cage set. Here we are, cage set array. Okay, so we're gonna have to add in an ID somewhere in here. So we have XYZ, and then we want ID just before frame. Okay, now what are we gonna want to do here? Basically, we want to say, let's see. We want to make sure that every single particle has its own ID. So we're going to say ID is going to be equal to. Now here's where things get a little bit annoying. We're going to have to pad each, each number with zeros. So it's going to have to be like, here, I'll show you. Let me go here, Blender-P, give it a second to run. Let me put it up here. And let me scroll down on the list of all the objects we have in the system. And you'll see we have a whole bunch of these cubes. We have, one second. cube 001, which is a big cube. Then we have smaller cubes within each of these guys. So let me zoom in, and you'll see, hey, look at that, we have all these smaller cubes in this system. And so basically all we have to do is go in and find the name of each of these cubes. Now what we can also do is name each of these cubes a particular thing. And I think that might be the better way to do it. So let me see. We've done this before with particles. So let me see, what do we have here? Parse data. Where are we? Move spheres. Numpart lines of data set. Max velocity, mid velocity. Let me go down to new sphere or something like that. Okay, here we are. Okay, so we have new sphere, and let me see, what do we have here? Material OB name. 1 second, I have to think here. ob.name is equal to string ID. That's what I want. So where are we here with cage set? Where are we? There's cage set. There it is. There it is. Okay. BPy data objects cube 0.01. Okay, so let's do this. Let's go ob.name. 1 second. Equals. Where am I? Yeah, so I want ob.name equals ID. There we go. So that we will read in an ID. And what do I want? I want bpy, all this stuff. But what I want to do is check this out, make sure it works. Let me go here. Let me go up to cage set real quick just to make sure I'm not doing something silly. And we're gonna say ID is going to be equal to how about we're gonna say cube and then I. Yeah, so cube. I think it goes something like this. So we'll say cube and then 1 second. And it should be, I think it's S, 1 second. And then I. Let's see if this works. Now let's go ahead and Blender-P. Did it work? It didn't seem to give me any problems. Oh, never mind, it did seem to give me the problems. Boxes did not appear. 1 second. Okay. Had to turn on the air conditioning, it's getting kind of hot in here. If you know what I mean. It's temperature, the temperature's warm. Alright, let me see, what do we have here? Cage set. Array 02. Oh, 83 is what I'm looking for. Let me go there to 83. And again, guys, if you have any questions, comments, concerns, let me know, and I will totally do my best to answer the question as soon as I see it. So we're going to go here, and we're going to say ID. It's going to be equal to C, 1 second, S, and we're going to say 0. And then we're going to go down here and say ID. Now we're going to do Blender-P. Looks like it went okay. And now let's go down and check the name of all these boxes. Okay, good. All the boxes now officially have a name to go with, which is great. Okay, now they might not be ordered appropriately, but that's okay. One thing I want to point out is there is something that's happening at frame 20. Here we go. So at frame 10, let me see. Okay, so it looks like at frame 10, this box appears. At frame 20, all the other boxes appear. Okay, so now we just have to kind of work with everything else. So we have the ID here. So what I want to do, I basically want to go down to, where are we? We want to go down to cage set. There, and there again. And what do I want to do? BPy ops object mode set. Let me see, BPy context object. Yep, so what I want to do then is go here. And I want to just go ahead and rename the object up here. Then I want to call in ID every time down there. So give me just a second. I can remove these lines here. I realize it's a little bit messy, guys, but that's okay. So now let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's just do 10x for all of these guys. Now let's go ahead and put an ID here. There, 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 and there. Now let's go over here, run blender-p. Give it a second to do its thing. Okay, now let's see what happens. We start with nothing. And let me just go ahead and zoom in and check to see what's actually happening in the rendered mode. Okay, here we have one box appearing. Then we have, again, I think... Oh, actually, I don't know what's happening. One second. There's one box. Okay, then all the other boxes appear. That's not what I wanted to see. I want to see all the boxes appearing at a particular time. So, let me see. What do we have here? Keyframe insert hide. Let me go up and make sure all the boxes are renamed real quick. And then we'll check what we need to do from there. Again, guys, as I mentioned yesterday, yeah, as I mentioned yesterday, I am working. I've got a whole bunch of stuff going on in real life, so these episodes might be a little bit relaxed. And if you have any questions or anything, let me know. Totally interested in hearing you guys' thoughts on things. It doesn't have to be necessarily related to what we're doing right here in stream. Could be about anything at all. So again, just let me know what your thoughts are. Totally willing to listen and hear what you got to say. So let me see here. Let me go up there one more time. Blender color quantization.pi. Sorry about that. Let me go here, zoom down. Let me check something. Let me see. Yes, all those keyframes are at 20, and I'm not exactly sure why. So let me go up here and let's check. 1 second. Let me go up to cage set. Here, this is what I want. Okay, so it should be that every 8, let me see. Yeah, it should be that every 8, how do I put it? Every 8 steps, we increase the frame by 10. So I guess what I'm going to do is I'm going to just output frame here. So let's do print frame. Do you think university is worth its value for computer science? I'm just waiting on getting 4. I'm just waiting on getting back. Wait, on 4 universities getting back to me to see if I'm in, but I feel I'm a lot further ahead that most courseware is providing. Yeah, so I'll be honest. Computer science is hit and miss from what I understand, depending on your university. I obviously studied physics. I didn't study computer science, but I know a lot of people who did study computer science, and they seem to think that even though they studied computer science in school, they still taught themselves how to code and everything like that. So it could be that, in some sense, you are ahead of the curriculum. In another sense, though, I have a friend who is currently doing a computer science degree, and he's mentioned the sheer amount of code that you need to be a good computer scientist. And he's saying the opposite. He's saying that there's no way you can cheat your way out of a computer science degree. However, as of the past week, he basically said that everyone just reads guides online anyway, and they don't really do the assignment. They just kind of use other people's code instead of their own code. So I don't know. It's hit and miss depending on what you're doing, I guess. Maybe someone who actually took a computer science degree would have a different opinion. But my opinion is that no matter what you do, if you do computer science, that degree will look pretty good. I mean, it's something that will definitely help you. But yeah, like what Gustrin is saying, CS for programming or software development job is not very useful if you're willing to do the self-learning. But let me think. Yeah, I think it is definitely useful in that it is a good degree to have under your belt. Whether it is the best degree to have, it's up for debate. Yeah, that's kind of your own thing there. So let me go ahead and run blender-b-p. And let me check something. So we should have a whole bunch of frames being printed out. 1 second. Of course we didn't. Probably because I misspelled print and I didn't write it. And let's do Blender-P. Yeah, so it stops at 20. Okay. So why would it stop at 20? Not quite sure. So let me see. I put that in parentheses. We should go through a whole bunch of different I values. So let me go ahead and also print out I minus 1. Print I minus 1. Let's go here, Blender-P. Yeah, so clearly we went through 423 particles, right? But it teaches some very useful stuff that you probably wouldn't learn on your own time. Complexity theory, algorithms. Yeah, I agree with that. Again, that's what I was saying before. I hear people on both sides of the spectrum, right? So it's not like there is a clear-cut answer. Let's go here, Blender-P. Okay, this one seemed to work okay. Yeah, okay, that one seemed to work okay. So now what do I want to do here? Let me do Blender-B-P here. And we should see, if I'm not mistaken, everything working the way I want it to work. So let's check here. Let's put it into a rendered mode. Oh, sorry about that. Rendered mode. I freaking hate mice. Zoom in a little bit. Okay, and let's go back here to the start. There are no boxes. Oh, here we are. 8 boxes. 8 more boxes. 8 more boxes. 1 second. Yeah, so we should be seeing, yeah, so we're seeing more boxes appear. I wonder if there's a way to better express how these boxes are appearing. Because at this point, we're just going to do that lower left box. And then we're going to do all the other boxes. Let me go ahead and go through. And let me see, what do I want to do? I want to make it so this isn't plus 10. This is instead plus 2. And then let me see, how many frames are we going to have in the simulation? Let me go ahead and, let's see, we have parse octree data. And at the end here, I want to return something. Let's see, where's parse octree data? Num2. Let's go up to parse octree data. Here. And there. And let's go ahead and return. Let me think here. Print frame. Frame equals 10. Yeah, so let's just go ahead and return frame. That should be okay. Now we go down to the bottom here. And let me go ahead and see what happens if we render a movie. I would replay the octree subdivision for the boxes. Yes, give me just 1 second. I was planning to replay it in a second. But what I want to do is render it as a movie first, because I figure that might help. So let me do Blender-B-P. And let me just see how long this takes. So here we have, yep, and then it should take a little bit longer than that. 1 second. Oh, let's do num2. And now let's do Blender-P-P. It should be a couple hundred frames. Give it just a second to do everything. From my little experience, I would say that you learn very little programming, but a lot of theory, and you will acquire deep understanding of compilers, OS algorithms, etc. The actual programming are very much learned by doing. I might be wrong, but I'm currently first year CS, so I am a newbie. Yeah, that's fair enough. Again, I kind of wish I would have taken courses on some of that stuff. Obviously, because I'm kind of struggling with a whole bunch of random things. And you guys see me struggling with a whole bunch of random things here. So Digita, every time you see me struggle, just think to yourself, if I was a computer science major, I probably would know what I'm doing. Okay, so let me go ahead and do an MPV. Out.mp4. Okay. Here we have all the boxes being created. Okay, so let's go ahead and see if we can slow down speed. 0.5. Okay, so there's our animation for the creation of the boxes. Let me try it a little bit slower. 2.5. Oh, how about we just do, yeah, 2, 5 should be okay. And then we're gonna do loop 0. Okay, let's go ahead and resize this guy. Bring it up here. Okay. 1 second. Which was pretty common trait amongst my courses. Wow, the first printed new £5 note is going for 65k? Holy cow. Okay, so this is about what I wanted to see. There's one thing I do kind of dislike about this animation. It's kind of small, but we can increase the size. That's not a big deal. We just have to bring the camera a little bit closer. I would also kind of like it to be flipped so we look at it from a different angle. But again, that's just nitpicking. It's something that we can change pretty easily. Now, let me think here. The one thing I'm kind of disliking about it is the fact that we are currently splitting up the boxes, well, I guess in the same way that we're currently going through the trees. You guys see what I'm saying? Like, we're going through the lower right box first, then or lower left box, I guess in this case. Then we're going through the upper left box, then we're going to the upper middle box and stuff like that. How do you authenticate it as the first note? I don't know, maybe the queen, I don't know what maybe does something. Okay, but this is good enough, I think. Let me think. So what I'm gonna do is I'm probably gonna go through and change our data. So let me go to 1 second, what am I thinking here? Cage set. Let me go down here to cage set. And let's do frame plus 10 like I was going to do before. And then what do I want to do? Then what I want to do is basically move the camera a little bit closer in. So what are we going to do with that? Basically, where do we put the camera data in? Where is the camera data? Camera. Ah, here we are. I've got a lot of different angles here. Screwed angle times 0.5. Skewed angle, sorry about that. So let's do skewed angle times 0.05. So let's move it in super close. 1 second, I need to, never mind, I'm just gonna pull up Julia for this. So let me do Julia. And let's see, so I'm gonna have to do 0.275 times 0. Let's just say divide by 3. Okay, so it's going to be 0.916. 916666. Down here we're going to do 4.0625. 40625 divided by 3. And this is going to be 13541. 66666. The next one's going to be, let me see, 0.18075 divided by 3, and this is going to be 0.06025. And we're going to change this to 0.05, and this might be a little bit too close, but that is okay. So let's go ahead and go here, and let's run. Oh yeah, let's just do the whole simulation one more time. Let's see what happens. Blender-HP. We're gonna have a lot of frames. I just realized that. Sorry about that, guys. It's gonna take just a little bit of time, and then we'll fix it up in just a second. Let me see. I don't know. It was probably noted on the news, so it got some attraction. Yeah, something serial number would probably make sense. Yeah, they normally like that in the UK, but I used my new note today, so I can't confirm the new note. Yes. So let me go and get some water. I should have left the frames as it was last time. That was my bad, guys. Sorry, I have a drinking problem. Okay, so give it some time. Yeah, so we have a conference here at OIST this week. It's called CQD, Coherent Quantum Dynamics, or something like that. It's for, basically for our lab, which does quantum systems and stuff like that. It's a super interesting conference. We have a bunch of incredible people coming. It's actually quite interesting how prestigious some of the people are that we were allowed to get here for lectures. Like it's in my opinion one of the best summer schools you could go to as a quantum physicist, or let's say a student in quantum physics. It's quite interesting, and I'm quite excited about it. However, again, that means that I just have less time to prepare all my streams, yada yada yada. So it comes with a price, but that's okay. Let's see, 500 frames that's a lot of frames. Let me go back to what I had before, because worst comes to worst. Let me see, what did I have before? Let me go down to cage set. There we are. And let's see. Let's just do 2 like we did before. From now on, at least for debugging purposes. Yeah. Are those the Brexit notes? Yeah. So I don't know what's happening with Brexit. I was kind of offended about Brexit when I heard about it the first time. Like, I was super surprised that the vote went through. Now I realize it's just kind of part of life, and I don't really know what to do about it, you know? So I'm not sure what people in Europe or the UK think about it. I don't know if they think it's a good thing or a bad thing. I generally don't see it portrayed positively, but I'm not sure. So, okay, there we go. There's all of our frames. Let's go ahead and run the last MPV. And actually, I just realized I'm going to have to quit that anyway and change the speed to what it was before. Okay, here we have all the boxes. We're a little bit too close. You will see that because if I move this in, we don't have the whole box appearing. But that's okay. That's something we can fix. For the most part, it's there. So we just have to move the camera out just a little bit more, and then we will be set. And I'm okay with that. We always do from then on is lower the size of the particles. And that should be about it. Hey Edge226, what is up? I'm doing fantastic, thanks for asking. Probably, but in my opinion, Brexit is going good. I got a raise and jobs are increasing while the house costs are dropping. This is before we have even left yet. I don't know, maybe that's, I don't know. Okay, so let's go here and ooh, what did I do there? That was not what I meant to do. Let me go down to where we do all the camera stuff one more time, and let's increase the size by, I don't know, 1.25. So let's open up Julia again. And let's do 0.0916. And let's multiply that by 1.25. Gives us 114. Let's do 1146. 46. Okay. And we're going to do the same thing for 0.1345. So 0.1354. 1666 times 1.25, and this is going to be 1 second, 1.69. Let me just grab this number. It's easier that way. And then we're going to grab this number, 1 second, and we're going to multiply it by 1.25, and then we get that number, and I'm just going to put that one in there because now I'm being lazy and just copying and pasting. It's okay. There we go. Write this, go over here, Control D, Blender-B-P, color quantization.py. Shouldn't take nearly as long as last time, and it is skewed. That is exactly what it says. Did I say screwed? I might have said screwed. It's skewed. Let me see. What did I miss? Well, most financial services are already in the transfer to move to other places, so yeah, it might be worse than it seems. Let's see. That's because you haven't left yet. Let me see. Yes, good. Good. As for more precarious, for us, more precarious is Italy, and they're approaching bankruptcy. Huh. You have a K instead of a C? Oh, I do, in all of these guys. Let me just go ahead and fix that real quick. And let's do skewed. Oh, sorry. With skewed. Oh. I apparently consistently misspelled it. 1 second. There we go. Now let's go here and let's take a look at this, and let's do speed 0.25. Oh, I misspelled speed. I'm misspelling everything. There we go. Take a look at this. We're gonna have to move the camera out just a little bit further. Sorry about that, guys. Let's see. But it's almost there. We have the octree being visualized. We have all the particles there. So now it's just a matter of getting everything appropriately visualized, and then we'll be done for now. Yeah, I know. I fixed the capital thing just a second ago. For some reason, I'm very bad at naming things. So we have to do this one more time. Let me see. Let's just do... I don't know. Hey, Fled from Nowhere. What's up? Right now, we're just kind of outputting octree stuff. Gustrun's here, but he's also, I think, in Happy Little Rats channel, if you're interested in talking to him in particular. Right now, we're just kind of visualizing some of the data that we have before for our visual color quantization stuff. So we'll see what we have from there. Uptime is 37 minutes. As always, I start at 5 o'clock in the morning, and we go from there. Okay, so let's see. What do I want here? Let me open up Julia one more time. Let's multiply each of these guys by 1.25 again. Hopefully that'll help. Let's do this times 1.25. And we get 1.4. 1 second. Here we are. Grab that. DD there. Take the next one, multiply that by 1.25. And I think this should put the camera in a pretty good spot. I think. Let's grab this. And let's multiply it by 1.25. Oh. Sorry, Gustron. I saw that you're watching Happy Little Rats too, and so I thought, I'm sorry. I just thought, yeah. Okay, so what do I want to do then? Let's go ahead and grab this and put it over here. 1 second. Okay, so now let's undo that. We're doing color quantization. I will describe it again in full detail in just a second. Let me go ahead and finish this up. Okay, 1.25, and then we should be good to go from there. I think this will be a good... Do you drink coffee? I do not actually drink coffee. I know that's kind of weird because like everyone in my lab definitely drinks coffee, but I do not. Control D. Blender one more time. Yeah, it's okay. I think the code works pretty well. It's just got a lot of bulk to it. I mean, we could cut down a good bit on just about everything. But I think it's fine. Sorry about that. Okay. Anyway. Is coffee bad? I've heard reports that coffee's good for you. Not that I really know, but, you know. I know that my parents used to drink coffee, and I like the smell of coffee. I just don't drink it, you know? The only thing I drink is water and milk, basically. Okay, so let's go here. Okay, good. So now we have all the boxes appearing. Everything seems good to go. We could probably drop the Z angle a little bit. Yeah, we could drop the Z angle. But everything else seems pretty good. So now let's just go ahead and change the color of all those guys. And then we're good to go. Is the best energy resource for us plebs. I'll be honest, like I just like water. It's something I enjoy. So let's change this to, how about let's do 1.11, and let's try it one more time. You must be a humanoid. Yeah, water is good, but coffee is good too, depending on what you want. Yeah, so the thing is, I never really got into caffeine because when I was younger, all the caffeinated beverages were also carbonated, and I don't really like the taste of carbonated stuff. It just, it scratches your throat as it goes down. It's just not my thing. And so I just never really got into caffeine, and so, I don't know, I guess, in some way, in some ways, I guess coffee just was never really appealing for me. Okay, so let's go here. I did it the opposite way, so let's change this to 0.8. And let's go here to Blender. Hey, happy little rat. How'd your stream go? Okay, give it a second to render. This is probably also a bad render, so let's see what happens when it's up, and then we will take a look from there. I'm not suggesting cocaine. Definitely not, if that's what you thought I was saying. No, not at all. I'm just saying that, powder your nose? Oh, is that what girls do in the bathroom? Cocaine? Probably not. Okay, so let's go to MPV. There doesn't seem to be anything. Let me see what happened to the camera with that one. I feel like I did something stupid here. Let's go to 0.9. Let's go to Blender one more time. My stream wasn't really a stream, just showing some macro horror to a macro hater. Ah, I see. So, yeah. Oh, I see what happened. Give this guy a second to render, and now I totally know what happened. I was off an order of magnitude. Oh, by the way, guys, I was in the middle of doing my simulation, like, for the past week, right? And, the code that I'm running uses, real units to do its simulation. So we use, like, you know, H bar and M and all these values are actually in the code itself. But for most people, when they do the simulation, they do it with unitless units. They say H bar equals M equals 1, and they don't really worry about what the units are. So all of my orders of magnitude are like 10 to the negative 32, whereas everyone else's orders of magnitude are about 1. And so I was running my code, and I couldn't get it to quite work, and I realized I was like a couple orders of magnitude off of what it needed to be. And so I just multiplied it by an arbitrary fudge factor, which is obviously representing some sort of unit that I missed, and it worked out just fine, but I have no idea what the unit is that I missed, because it's like 10 to the 5th or something. Oh, maybe it's the number of particles. Thanks, guys. That might be exactly what it is. Okay, and there we go. That is our visualization of the octree. I think it works quite well. Okay, so now, guys, I will take a step back and talk about what exactly we did. There are a couple things about this visualization I'm not exactly happy about, but in the end, we do get a full octree, and I think it looks okay. Yeah, so I think if this was like randomly dispersed particles, I think it'd be pretty good. Yeah, I think it'd be pretty good. So let's go ahead and close this. Just remember how floating point works? Well, yeah, but I don't think it was a floating point precision problem. I'm pretty sure it wasn't anyway. I mean, I guess I was using a gaming card, right, instead of the graphics card we have on the cluster. So the best it could support is float instead of double, but I'm not sure. You can actually write some pretty neat stuff with custom types that actually represent units and user-defined literals in C++14. Yes. I think I could imagine people doing something like that. Okay, so that's fine. The last thing I need to do is change the... One second. What am I going to do here? Oh, change the size of each of the particles. That's what I need to do. So what are we doing here? New sphere Monte Carlo should be what it is. Where are we? New sphere Monte Carlo. There we are. So let's go ahead and change this from 0.01 to a 0.005. From this, go here and make that, and let's see what happens. Floats are pretty tight in range comparison to what you have used. Very limited, actually. I don't know exactly what you mean. What do you mean pretty tight in range? You can write 0. Oh, that's actually quite useful. Yeah, so we could do like meters per second or something like that. Yeah, I might look into that. I'm already using those in my engine. Yeah, so let me go here and let me see. Now let's do MPV. So the dots are kind of small, but they're better for quantization. Because now they actually fit in all of their individual boxes. Not sure. So I kind of like them a little bit bigger anyway, so let's just kind of leave them a little bit big. Now, we have to do one more thing before we're done here. So if you missed some units, it's a compiler time error. Just noticed I no longer remember how I found your stream. Probably browsing Twitch programming category. That's how most people found it. Either that or it's from YouTube. Some people found it via YouTube. let me see, I'm already using a 24-bit mantissa. What is a mantissa? Sorry about that, I don't know that word. That's only 16.7 actual values per range. Multiplying different exponents will lose precision very fast. Yeah. Okay. So now what do I want to do? I want to create a very quick image with a whole bunch of different colors in it. Or I want to change the particle data that I'm reading in for this particular image. I feel like that's what I want to do. Okay, so let's go here. Run quit. And let me do, what do I want here? Color quantization.py. Yeah, it should be okay. So let's go into color quantization.cpp. I'm gonna do something stupid. What got me into streaming on Twitch? I will answer that question in just a second. Let me go ahead and find what I'm looking for down here. There we go, that's what I want. Okay, so we're gonna do an image read. And then we wanna do this line right here. Oh, you guys are gonna hate this. This is just the easiest way to do it. Yeah, what's your motivation? Oh, so I kind of mentioned this after last week. So, actually, lots of things have been happening, which make me want to continue streaming, but they're all happening in real life, not necessarily on stream. So, while on stream, I learned things that I would never learn in real life. For example, well, we've already, Maxwell's Demon was kind of an exception because I had already done Maxwell's Demon before, and it was just kind of me rewriting the code, which ended up being good because, you know, I learned a whole bunch about optimization and stuff like that. But the optics stuff I never would have done had it not been for this stream. The quantum information stuff I never would have done had it not been for this stream. Barnes-Hut algorithm, octree quantization, all this kind of stuff I never would have done had it not been for this stream. And so basically the idea is I'm coming on here every day and I just kind of, you know, learn something, right? And that's kind of motivation in and of itself. But lately, because I've been kind of putting my stuff on my YouTube channel, and a lot of people in real life watch my YouTube channel, they stop by and they're like, hey, how would I do this? And I can actually answer their questions. Like, for example, one of my friends came by the other day and they said, hey, I have this system of electrons that I want to treat semi-classically. How do I work with that? And what I realized was I actually could answer the question because I had spent a whole bunch of my time, basically all of my free time, learning how to do random simulations for no apparent reason. And so, in the end, my motivations to continue are a little selfish in that I'm doing it so that I can keep, you know, so I can continually learn more about different algorithms and things like that that are used in physics. If at some point I feel like my knowledge is sufficiently high, I might stop streaming at that point, but I don't see that happening because no matter what, there's going to be someone better than I am. And so the idea is if I continue streaming, I continue programming, at some point I will become better at what I'm doing. And that's definitely showing in my research right now. I'm becoming better and better at my programming and research and stuff like that. So that's kind of where I'm at there. I'm learning by doing. And Fled from Nowhere, I would like to point out that I don't really consider this teaching. It's more or less me just learning, and you guys are here for the ride. So you guys are learning with me, is what I see it as. Let's see, mantissa is numerical value stored by float normalized to exponent. Oh, okay. Yeah. Open link. Whatever computer science knows about floating point arithmetic. There's one. Okay. Older term is what it says. Okay, so now what do I want to do here? Let me go ahead and change this to pvec.size. And this should create a random image. Let's go over here and let's do a make. So hopefully that answered your question. Hopefully that answered your question to why I continue streaming. I realize it's kind of a hard question to answer, but that was it. I just do it because it helps me learn things that I wouldn't learn otherwise. So now let me go ahead and open up Mirage out.bmp, and let's zoom in. You'll see that we have a whole bunch of random dots, exactly like what I wanted. So now if we do our Blender quantization algorithm, we should have a whole bunch of random particles just dispersed in space. Actually, a small gist where I collected some interesting floating point stuff. Yeah, I need to learn more about that kind of stuff. Like, I'll be honest, like, a lot of this stuff, again, because I don't have a formal computer science background, and actually, this goes back to what we were talking before with Digita. When I was going to, study computer science, let me go ahead and go here. Yeah, so there's all of our particles. Yeah, okay, this looks quite good. Sure. Okay, yeah, this is okay. Oh, I'm seeing that now. Okay. Anyway, so as we were talking about with Digita earlier, when I initially entered college, I had no intention to become a computer science major. Like, I had no intention to do programming again or anything like that. In fact, I intended to become an author. However, that didn't quite work out. I took a physics class, and then I was immediately interested in physics. And then that led me back to numerics, which made it so that at some point, I had to relearn programming and stuff like that, which was good for me. I was glad I had to relearn it. Now, one thing I want to point out is because I was already, I already knew a good bit of programming, all of the computer science courses were somehow beginner courses. And I had to take the beginners courses before going on to the advanced courses. And I just didn't have time to take all the beginners courses because by that time it is junior year in college. So if I would have taken the beginners courses and then going on to the advanced courses, I would have had to take another year of undergrad. And that wasn't worth it to me. So kind of the reason I didn't do my computer science stuff is because of the same reason Digita was saying earlier. It kind of felt like I'd have to take a step back before taking a step forward. And that was kind of the reasoning there. Okay, I've got a feeling I did something stupid here. Let me go here and let me do color quantization.py. Let me go down here and let me just not render the movie this time. Now let's go in and let's do blender-p color quantization.py so it opens it up in the Blender thing. And let me check something because I've got a feeling that there's something weird going on here with all these particles. So let me do here, rendered. And let me see. Oh, this is actually kind of hard to see, isn't it? I'm trying to tell if each of these particles has a clear and defined box to be in. But I don't know if I can tell that. Oh, it doesn't look like they do. Dang, this is actually kind of hard to see. Maybe what I need to do... Oh, it looks like they might, though. Yeah, okay, I think they do. I think it was just the way that I was seeing it before. Okay, let me see. And there's also one more thing that is kind of bugging me. Oh, never mind. That's just how I'm looking at it. Okay, so I think this is a physical simulation then, or like it is correct. I think it's kind of hard to really tell, which means that I should probably let me take a look at the visualization one more time. So let's go here and let's take a look at MPV here, and let's see. We have our box. It's creating a whole bunch of smaller boxes. Yeah, I'm okay with this, I guess. So let me go back to the start. There we go. So there's our first box. There's our second box. Yeah, so I guess as long as I can separate each of these images. So I can like kind of show each of these images popping up, something like this. I suppose that's fine, right? Yeah, so yeah, this should be okay, I think. We'll see how it goes. At worst, it gets the point across. I hope I didn't miss anything in chat. If I did, let me see. Nice approach to learn. Yes, okay. Good, so at this point, guys, I think the color quantization is done. So let me go ahead and, yeah, let me do something then. Let me go into rank quit. Rank quit. Let me go into, Oh heck, what do I want to do? Let me go into colorquantization.cpp and let me try a bit of a longer simulation here with flower power 4 instead of flower power 5. It's a little bit bigger. Right, this, go over here, and let's do, 1 second, right quit, go over here, and let's make that. Give it just a second to do the making. It shouldn't take so long, probably a little bit less than, yep, that's what I was expecting. Now let's run blender-b-p, and let's see what this looks like. Okay, let's go into colorquantization.py, and let's actually render the movie this time, right here, and let's run that. Okay, so I don't know how many frames this is gonna be, but it should be a good number. So we'll see what we have here. I'm gonna guess, oh, I don't know. How many should we guess here? 200? No, it's gonna be more than 200. Maybe 500? Not sure. Actually, maybe I should have thought about this before running the simulation. Okay, so 250 is what we've got. I really should have thought about that beforehand. So we'll let this guy run, and then we'll move on to the next thing. So I will do a quick wrap up of the color quantization, and then we'll get back to the kind of stuff that I'm not very good at, which is the OpenGL stuff. And we'll see what we need to do from there. So there's a whole bunch of stuff here that I'm kind of skimping over, and I'll be honest, the OpenGL stuff is kind of, it's kind of hard for me. So it's going to be a little bit messy and a little bit boring, and I'm letting you guys know that ahead of time. Like I said at the start of this episode, a lot of today is going to be a little bit slow. A lot of it's going to be a little bit slow. Not sure, it looks like flipping a sign. By the way, open link. What do we have here? Oh, I see. Oh, I didn't even know there was such a thing as a volatile float. I didn't know that was a type. Okay, we'll keep letting this render. It shouldn't take so much longer. I'm going to guess another few minutes, and then we should be good to go from there. Again, guys, if you have any questions, comments, concerns, let me know in chat. The only way I can really tell if you guys are here or not is whether you say something in chat. So I'm not saying that, you know, I mean, if you're lurking, I have no problem with that. Lurkers are great. But, yep. Yep. I'm gonna get a quick sip of water. Okay, good. But when you say don't assume anything about this, let's see. Something else could changing it. Oh, I see. So now let's go ahead and run MPV. And let's see what we got. So here's all of our particles. We see all the little boxes being created. Yeah, good. And we clearly see the image too. This is great. So the color splatter that you see right here corresponds to an image that I'll show you in just a second. It's kind of a small image, but that's okay. So let me see, what do we have? Sure, okay, I'm okay with this visualization. It shows what the Octree is. We can slow it down. Should be okay. And then the image that we're talking about right here is, let me see, Mirage out.bmp. Scroll in. It's literally just a whole bunch of random points. And that's all it is. And that's good. So we have a whole bunch of random points here. We have the visualization there. So let me just go ahead and I'm going to move this over chat for just a second. And then we're going to quit here. And we're going to run MPV. And let's do out.mp4. And what do I want? I want to do out.mp4. And let's do loop 0. And let's see what we have here. There we go. Okay, so here is the Octree data that represents this image over here. Again, this could be done a lot faster, I get that, but it's okay. It's okay. Okay, so I'm okay with this. This worked quite well. I'll be using this Octree visualization for a number of different things later on. So we'll see how that goes. So let me just go ahead and do a quick wrap up with Zernal, and then we will talk about what we're doing next. 1 second. I'm actually quite happy with that. That looks pretty good. Now, I gotta admit, it's not like the coolest visualization I've ever made. And I'll be honest, the color quantization video, I'm not expecting to be like the #1 video I've ever made on the channel, but it is laying down the groundwork for what we're doing next, which is galaxy simulation. So, let's go ahead and go down here, and let's talk about it. So, in case you guys are not aware, and I definitely apologize for waiting so long for this, let me do new page before, and let me just very quickly talk about what we just did. So what we did is we took an image, and we took every single pixel in the image, and we treated RGB as X, Y, and Z. So we treated red as the X dimension, green as the Y dimension, and blue as the Z dimension. Then we plotted all of the particles onto a grid. So what you just saw was us parsing the grid into something known as an octree. Okay, now this octree has a heck of a lot of uses, and it's quite important to keep in mind. Now, after we parse it into the octree, the question is, why do we want it in that form? Well, for us, what we were doing just then was something known as color quantization, where we reduce the number of colors in an image with the intent that people cannot see basically the difference between the quantized image after we remove the colors and the non-quantized image, which is the one that we had to start with. So, for example, let's go ahead and run a color quantization on a rather large image, and I'll show you exactly what it will do. So let me go ahead and go into VI color quantization.cpp, and let's go down to PVEC. Here we are. There, so let's go ahead and not randomize this. And let's go ahead and read in the appropriate image, which is regular old flower power here. It's just a flower that we're working with. Oh, you. And let's change the number of colors to, let's say, 16. Oh, let's get crazy here. 64. And we'll make that. It'll take some time. Not that long, maybe about 10-20 seconds. And then we should be good to go from there. But basically the idea here... Yes, so basically the idea here is that we are limiting the number of colors in the image. So originally the number of colors was like, I don't know, the size of our P vector, which is 800 by 600. So we'll say, how about 500 by 500, 125, 1 million, basically 1 million colors, we'll say. 1 million colors. And we limited it to the 64 most popular colors. By doing this limitation, we obviously have a fewer number of colors to deal with. And if we open up the output image, we see, okay, well the image isn't really that great, but we do have significantly fewer images than we had before, which would be what we see in this image here. .png. Now obviously if we run this one more time, and we change this 64 to, let's say, 512, and then we run that, we'll see that the image is pretty dang close to what it's supposed to be, and that's pretty cool. This means that we've limited basically 1 million different colors to just the 512 most popular, and it looks pretty much like the image we want. And if we're shrinking the image down, or we have a limited storage space to save data onto, this is good to do, because it allows us to basically show the exact image we want with fewer colors. And that's pretty cool. Now there's a whole bunch of other things that we can do here with the color quantization code, but again, this was basically a cool application to the octree, like we were saying before. And that's pretty cool. So let's go ahead and do Mirage flowerpower.png over here. Here's the original image. And here, Mirage out.bmp is the image after quantization. And you'll see it looks pretty dang close. And that's pretty good. Random ASCII WordPress, floating point. And that's kind of what we're doing with the color quantization code. So what you were seeing just before with the visualization was basically us parsing the data into an octree so that we can more easily represent every particle inside of the boxes as, well, a general color. So we are basically quantizing the color. We're saying that anything that is partially red goes in the red box, anything that's partially blue goes in the blue box, so on and so forth, so that we can more easily split the colors up. And that's kind of what we're doing there. So let me see. I'm familiar with that. The blog in general is pretty great. I guess I'll take a look. Everything's old new again. Oh, floating point determination. Determinism. Okay. So, let me go down here. And let's talk about that. So the color quantization, again, basically all we're doing is we're taking all the points in space, we're putting them into a quad tree or octree, and then we're saying all the particles that are within each of these boxes are the color of the center of mass of the bigger box it's in. So this guy is no longer, let's say it was this color blue before, it's now this color blue over here. We've changed all of the blues to be this blue over here. So sure, this leads to some error, but the trick is finding the best way to represent all of the color in the image such that people don't notice that we've quantized the color. And in that case, it doesn't matter. We've basically saved on data, and we have also not changed the image for most people looking at it. So it's kind of interesting. Now, what are we doing next? Okay, so next we're going to get back into our galaxy simulation. Kind of. I'll be honest, when I say we're getting back into our galaxy simulation, the simulation is pretty much done at this point. We have the Barnsdot algorithm, I think, working. From what we plotted with NuPlot, it looks fine. But what we need is an actual video visualization of this. So what are we doing for that? We are going to be doing OpenGL. Now, I'll be honest, the last 2 times I tried this, it failed miserably, which is why I tacked it on to the end of this episode, hoping that I can get it done quickly. Basically what we need to do is create an OpenGL sphere. And truth be told, this is not hard. It's just because I've never done anything with OpenGL before, it's kind of difficult for me. So here's the idea. In order to create the sphere, what we're going to do is we're going to first create a triangle of triangles. And then from there, we're going to basically blow out this triangle. So for example, imagine that this triangle is kind of leaning like this, and we have the central radius here. The idea is that we then force all of the vertices in our triangle to be a particular distance d, or let's say r, from this point here. So they're all of radius r away. And so then all we do is a quick transformation on our triangle of triangles, that again is over here, to turn it into a curved circle, or let's say quadrant of a circle. Now, what I want to get done by the end of today is basically this dang triangle of triangle thing. So first of all, let's talk about triangle numbers. Okay, so triangle numbers are basically, let's put it this way. If we have a triangle of triangles, that was a horrible triangle. 1 second. If we have a triangle of triangles, let's go ahead and just draw some lines here. Something like this. Forgive me for this being a very bad drawing, but I'm not an artist, so I think that's okay. Okay, so we have one triangle here. And let me see here. So we have 1, 2, 3. 1, 2, 3. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so 1, 3, 6, 10, 15. 3 is equal to 1 plus 2 is equal to 1 plus 2 plus 3. 1 plus 2 plus 3 plus 4. 1 second. 1 plus 2 plus 3 plus 4 plus 5. These guys right here, 1, 3, 6, 10, 15, those are triangle numbers. They are numbers that are specifically known in mathematics as following the triangle number sequence or whatever. Now, you might ask yourselves, what's this down here? So this is going to be 2, this is going to be 4, 7, and 11. So, going along one way, we have all the triangle numbers. Going along the other way, we have all the triangle numbers plus 1. Okay, so what we're going to try real quick, in order to get this triangle of triangle thing working, and I'll be honest, it might not work in the end still, is we're going to keep 2 different counts. We're going to keep a top count and bottom count of each of these different rows, okay? And forgive me if I'm moving too fast, or if you guys don't understand, just feel free to ask questions, and I will do my best to answer those questions as soon as I see them in chat. Okay, so what are we doing here? We're going to keep a top count and bottom count. So we'll say top count here is going to be equal to 1, bottom count is going to be equal to 2. And then what we do is we go through and we say, while our bottom count, this count down here at the bottom, is less than the total number of triangles in our system, so we'll say 15 in this case, we're actually just going to increment the bottom count first, and then the top count. So we'll say, okay, 2, 3. So we'll say 1, 2, 3 is our first triangle right here. So that means, in the end, the top count is going to be 3. It's going to be up here. The bottom count is going to be 3. Then we add 1 down here to get to 4. Okay? Top count. After we do B count plus plus, after we add to the B count, we then say that the top count is equal to the very last row number, or the very last triangle number plus 1. So that means the next one's going to be 2. So row number is... I'm doing a very bad job of describing this. So the very last triangle number plus 1 is going to be the last top count. So we're going to say 2 here. And so then we basically say, okay, we have 4 here. So then it's going to be 4, 2, 5. That's going to be the first triangle. The next triangle is going to be 2, 3, 5. And the next triangle is going to be 3, 5, 6. So basically we just continually go through by just flipping the triangle along. I think you'll see how this works in just a second as we implement it in code. Again, I have my pseudocode here, so hopefully this will work out okay. If not, it's okay. We'll see how far this goes. Again, this is another situation where I kind of feel like we're learning this as we go along. So start from index 0. Starting from index 0 makes this... we just have to do -1. That's fine, we can do that. But, let me see. So starting from index 0 just means... yeah. Let me think. 0, 1, 2, 3, 4, 5... Okay, so starting from index 0 makes it so that this guy right here, the triangle numbers are on this side, and... the triangle numbers are on this side, and triangle number plus 1 are on this side. I think. Let me redo that. New page before. Well, it does kind of change how we do this, right? So let me check something real quick. So if we have a triangle, 1 second. Here we are. Then we go, hey, Tessie, what's up? 1 second. That was a horrible triangle, I understand. So if we do 0, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so the triangle numbers are on that side. Okay. Good. Okay, so let's go from there. Again, I couldn't really find a good enumeration scheme online. I did look it up. They didn't really have... maybe I just didn't look in the right spot. But that's okay. So color quantization for now I think is done. We have all the visualizations we need. Let's go ahead and move on to the OpenGL stuff. So we're going to cd dot into OpenGL. And we're going to go here and we're going to cd back into OpenGL. And let me just go ahead and make it and show you guys what we have right now. So right now we have basically nothing. Because if we go back into our code, so let me do ls and let me open up simplegl.cpp. And let's go down here. Okay. So what are we doing here? I've changed a couple of things since the last time you saw the code, but for the most part it's the same thing. Let's go down here to the bottom. Subdivision is usually done in a different way. How would... Dagnabbit. Okay, so maybe I should just quit here. Man, that's super unfortunate. So I can look it up again. I don't see how you do it with recursion at all. I have no idea. And again, I couldn't really find any links, so maybe if I... Let me try it again. Let me just Google creating a triangle of triangles. And let me see what we got. Make a perfect triangle. Let me see. OpenGL. You see, like, we get these things that are just like, I draw one triangle. But, like, I can't see... Let me see. So divide each edge into 2 equal parts and generate 4 triangles. Divide each edge. Let me see. So what you're saying is start with a triangle. New page before. Start with a triangle. And then you say divide each each edge into 2 equal parts and generate 4 triangles. Okay, so you're saying do this. I see. Okay. No, I see what you're saying. Then you just continually divide it again and again. Okay, so now I'm trying to figure out how the enumeration would go here. So we'd have 1, 2, 3. Then we'd have maybe 4, 5, 6. Then we'd have 7, 8, 9. Ten, 11, 12. How would you optimize it exactly? Okay, so I think actually this is probably a little bit easier than what I was doing anyway. Although, let me think. Yeah, so what this would mean is we have the boundary triangle on the outside. Okay, good. So this is actually tremendously, I think, well, no, it's... Let me think. I don't know if this is any faster than the way I was planning to do it, but we'll see. Let me see. Okay, I'm just looking at the code that I wrote. Yeah, we can try the recursion thing. We'll see how that works. Or recursion needs to be controlled to have localized indices as possible. I don't know what you mean by as localized indices as possible. Sorry about that. I'm not following that logic. Let me see. Okay, so we'll try it with recursively, and we'll see what we get from there. Okay. Hey, Galvabart, what's up? Okay, so what do I want to do then? Let's see. I want to then go ahead and draw a single triangle, and then we'll recursively generate all the smaller triangles from there. And then what we can do... Let me think. Yeah, okay, so this should be relatively straightforward then. So what I want to do then is, let's see, create triangle vertex. Let me go ahead and comment out what I currently have. Let's go here, DD there, and let's go here. Okay, so what are we currently reading in? We're reading in vertices and indices, but these have nothing in them at all. So, oh, wait a minute. Let me think. Okay, so the way I have this set, I'm actually kind of curious here. I don't know how this works. Let me go ahead and DD here, and let me do this real quick. Now let me try something. Let me reserve this and vertices dot reserve. I don't know if this is gonna break or not. Num vertex divided by 2 plus 1. Go here and let's do make. Okay, so that seemed to be okay. I wasn't sure if we were allowed to reserve twice after each other like that. I didn't remember. Okay, so let's go here. And let's go here. Okay. So let's go ahead and generate our first triangle one more time. and then we will go from there. So what do we want here? We have int resolution. What is resolution here? In the end, we'll have the same number. Resolution should be the depth that we go then. Let me think here. So if we are splitting up the triangle recursively, page, new page before, and we have a depth of 1, I want to see if these relate to the triangle numbers or not. I have no idea. So I know the formula to get your triangle number is going to be n plus 1 times n over 2. Okay? So if we are at 1, so if n equals 1, then let's say t equals 1. If n equals 2, then t equals, let's see, 2 plus 1 times 2, 6 over 3, 3. If n equals 3, t equals, should be 6. Good. Galvabar, what we're doing right now is we are basically generating a triangle of triangles in OpenGL such that we can then turn that into a sphere for the visualization of our, how do I put it? For visualization of our Galaxy Simulator that we've already done. So we've already kind of worked with the Barnes-Hut algorithm, and now it's a matter of plugging in everything from there. So I apologize. This is kind of, meshing and stuff like that isn't really easy for me. However, I did recently pick up a book on meshing, so I may go through that at some point on the channel too. Okay, so now let's check out the triangle. Happy Little Rat was saying that we should do it recursively. So if we split these guys in 2, 1, 2, 3, what numbers do we have here? We have, let me see. We have 4 triangles there. I'm trying to figure out how many we have to reserve, how many points we have to reserve. Okay, so if we go through, this is this isn't easy exactly, but basically if we go through and we say, let's see, if we start at 0, 0, 1, 2, then this is going to be 3, 4, and 5. Which doesn't help any. It's not at all related to triangle numbers. So we're just going to have to reserve our vertices as we go through. So every time we create a new triangle, we're just going to have to reserve 6 more. Oh wait, maybe it is related. No, it's not. So our number of vertices is going to be equal to, let's see, here it's going to be equal to 3. And if it's a depth of 1, it's going to be 6. If it's a depth of 2, one second, something like this. So 4, 5, 6, 7, 8. Oh. This means we double count certain points, though. Yeah, it totally means we double count certain points. Let me see. Here, let me do it the other way first. Oh, the way that I was planning to do it to begin with. See if that works, and then I'll worry about the recursion thing for after that. Because at this point, you know, the recursive solution obviously didn't come to me at the time, and I'm not seeing how we don't double count vertices right here. So let me go ahead and do it the other way I was planning to do it, and then we'll go back through and we will do it the other way later. Sorry about that. It's just, wait, double counting is the best? I'm sorry, I'm not... Wait. What do you mean that's the best? Doing it my way and then coming back to the recursion? Or... I'm not sure if I fully follow. Okay, let's go ahead and remove this. And let me go back to what we have before. So we have this for defining the indices. And like I was saying before, let's just do what I was planning to do. If it works, it works. If it doesn't, it doesn't. Sorry about that. So we'll get back to the recursive solution before, because it seems like that might be faster. But let's get something working first, and then we'll go from there. Okay, so what are we going to do? Let's go here. And let's go ahead and create a couple integers. So we're going to create int top count. And then we want... yeah, sorry about that. Again, this is one of those things where I wish I was a little bit better at doing this kind of stuff, but I'm just not. And what else do I want? Then I want row count. Okay, so this is what I want. Top count, bottom count, and I might as well just say R count. Fine, we'll say top count. And bottom count. And then row count. Okay, there we go. So we have that. I'm assuming that our vertex enumeration or things works above for this to work okay here. But we'll see if that's working, because I've got a feeling these locations are not quite right, but we'll see what we need to do there. Okay, so what are we going to do first? We're going to say while bottom count is less than the number of total, the number of vertices total, which is going to be 15, I believe. So let's see, num vertex. Yep. So I'm going to say num vertex. We are going to get into this loop. There's several layers of complexity on top of what you're currently doing. If you wish to generate optimal results for a sphere, for example. Yeah, so there's multiple ways that we could do this. This is just one way to do it. You can delete all calls to vector.reserve in your code, since you're doing pushback already. Yeah, but the reserve speeds up the pushback. Yeah. Right? Am I doing that wrong? I was pretty sure that the dot reserve speeds that up. Okay, now let me see. Well, bot count less than number of vertex. Here's what we're going to do. We're going to say top count is going to be equal to. So you don't need to try to compute up front how many vertices or indices the algorithm is generating. Continuous life will. It's fine. It's fine. I'm not a beginner programmer. It's just the first time I've done OpenGL. So don't worry about that. Okay, and so we got top count here. No, this is fine. This is fine. It's good as it is. Right now I know that top part works. Good. So let's go ahead and do top count is going to be equal to the triangle number, which I'm going to create a separate function for the triangle number. So let's go ahead and create, 1 second, let me do an ls over here, and let me open up simple GL. 1 second, simple GL.h. Oh, do I not have a .h? I do have a .h, but nothing is in there. That is okay. So let me think here. What am I currently compiling this with then? If we go to the top, we have vec.h and shader.h. Void, oh, I'm defining it up here. That's fine, fair enough. Let's do it here too. So we're going to say function to return a triangle number. 1 second. When provided an integer. And I realize this is like a super... Yeah, I dropped that idea for now, just because I'm just going to do it another way, and then we'll get back to the recursion later. The problem, I was just going through the recursion a second ago on Zernal, and it was kind of bugging me that we'd have to redefine certain vertices, so I have to kind of think about how to do that without having to redefine the vertices. Because I don't like having to redefine vertices. I find that kind of weird. So we'd have to think about that. And so right now, since we have stuff that's kind of sort of working already, let's go ahead and use that, and then we'll go from there. And then I can write out some pseudocode or something like that for the recursion thing later. So we're going to say, what do I want here? I'm going to return back an integer. How about a double? Double should work. What do I want? No, int should work. Int should be okay. Int, and I'm going to say triangle number. And then I want to read an int n. Why not? So it'll be fine. And we're basically going to say return. And what do I want? I want n. Let's do n times n plus 1 divided by 2. Okay, but let's not go there yet. I'll explain it when you get this done. In case you're looking at the recursive subdivision at some point. If you want to do recursive d times starting from one triangle, there'll be 4 d triangles. Yes, that sounds about right. Okay, so let's go down here to the bottom again, and let's go ahead and define what we need. So what we're going to say, where are we here? Here we are here. We're going to say t count is going to be equal to triangle number. 1 second. Of row number minus 1. So these will be good numbers for the vector.reserve. All right, good. I appreciate that. So let's go ahead and define row count. Oh. 1 second. There, and we're going to define it as 1. Okay, so this means that we will start at 0 for the top count, and starting at 1 for the lower count, I think. Again, guys, I appreciate all the help. We're just going to go ahead and get this done this way, and then I'll go ahead and think about how to do the recursive solution a little bit later. Again, it's little things here and there that I'm not sure I fully understand, and I'd rather not implement something from scratch when I have already thought about something on my own time. So we'll do that, and let me think here. So we want actually to start bottom count at whatever it was before plus 1. So we will say, how about we start row count at 2, just so that we have something to start with. This means that our first triangle number will be 1, and we're going to go ahead and start b count equals 1. Then we'll go down here and we'll say bot count. I'm doing a very bad job of keeping notation here. Is going to be equal, let's do bot count plus plus. That'll work. Now what we'll do is we'll go down here and we'll say, go to the next level. We'll say while. 1 second. We also want to set I equals 0 here. And now we're going to say while, oh my gosh, I am just screwing up miserably. While b count, bot count is less than the triangle number for our row number. One second. We go here and we say if I mod 2 equals 0, we're working with a upward facing triangle, and we're going to say if I mod 2, let's just do else. That'll do it too. Else. Okay, and let me go ahead and write in some comments here while we are thinking about it. I think we should be able to get this done pretty easily in, like, I don't know, the next 10 minutes. So let me just go ahead and write some quick comments. This is done by keeping track of, let's see, every row and incrementing the top and bottom counts. And let's go down here and say upward facing triangle. And then we're going to say downward facing triangle. 1 second. If I can spell facing triangle. Okay, now let's see, what do I want to do? So we have this, now we want to do an I++ at the end here. Okay, so this is kind of what we're doing, right? I is going to be for every individual row. We reset it at the start of every row, and then we just kind of move our characters through. So next we're going to say, we need to put in the appropriate indices. So how are we doing that before? Let's see. Before we were saying indices AB is AB count, BC is BC count, CA is CA count. Let me see. How exactly was I doing that? Oh, I see. So I had 3 different indices, A, B. Yeah, okay. Let me see then. So then all I'm going to do is go up here, and we will say the following. So we're going to say indices of I.ab is going to be equal to, let's do top count indices of I dot BC is going to be equal to, and this one should be bottom count. And then we do indices of I dot CA equal to bottom count plus 1. Okay, then at the end we do B count plus plus. Okay, now we do the opposite for the top case. So let's just go ahead and grab these guys here, copy it down here, and change these to bottom count and top count. So we're going to do top count plus 1, plus 1, and then we want to do bottom count as it is. Change this to top count plus plus, and let's go ahead and DD there. Okay, so now what I want to do is run it. Okay, triangle number was not declared in the scope. Triangle number. Okay, I called it triangle num. It needs to be triangle number. Let's go ahead and write this, and let's go to make. Okay, we have one triangle. It's I don't know what it's doing, but we have one triangle. Let's go and close that. Okay, so let me think real quick. Let me go up to where we define our indices, because I've got a feeling. Let me see here real quick. Indices, vertices, indices. Where do I define them? Oh, okay. I define it as one index. So let's go through here and let's change this up a little bit. So instead, I'm going to define it like I did before, and I'm going to reserve the space in here. So we'll go ahead and reserve the space up here, like what I was doing before. And let's see, if we have 15 vertices, how many triangles does that mean? That means we have, 1 second, 5 triangles. What? No way. 1, 2, 3, 4, 5, 6. Yeah, that's clearly... Wait, let me think. Okay. 0, 6, 3... Wait. Let me go back. Okay, here we are. So for 15, we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's not right. Where is my last image? Okay, here we are, 15. How many triangles do we have here? 1 plus 3 plus 5 plus 7. So 1 plus 3 plus 5 plus 7 triangles. What is that? How many triangles is that total? Let's see. So if we have 15, how many rows are we gonna have? Ah, gosh darn it, I'm not sure. So I guess what I can do instead. Oh, no, I don't want to do that. Let me think here. Let me just increase the number of indices that we have. Oh, shoot. I just realized something. I need 2 different indexes to work with here. Otherwise, I just continually redefine. 1 second. I gotta think here. So this is gonna be our row count. I is equal to 0. So we reset I equals 0 every row. Yes. And then, let me think here. We probably don't need to reset I equals 0 every row. 1, 3, 5. Oh yeah, we do. Yeah, we definitely do. Okay, so if I want to, then what I'm going to do is this. I'm going to create a separate count over here, which is J. And actually, let's just change this. So this is going to be J. And this is going to be J. This is going to be J. And then I want to go up here and I want to say int I equals 0. And change this to a J here. And then we want to do over here, I++. And these guys are going to be of I. Good. So now what I want to do is reserve the appropriate space. So let's go up here and let's say, what did I call it? Index or something like that? I think I created a separate class for index. Let me go up here to top. Where am I? Where did I keep all my structs? Invec.h? H. And let's see, what do we have here? Struct triangle. Good, okay, so we have triangle. Let's go down here. So I'm gonna create triangle, temp triangle. We're gonna do triangle, temp triangle. Okay. And then we're gonna go here and we're going to say, and actually this will be fine. So we're gonna say temp triangle is going to, dot AB. Oh, screw it. Let's just do it this way. Copy these guys. Put them here. And then we're gonna do 10x. Same thing here. We're gonna say temp triangle. And do that here again. And there again. And we're gonna do indices.pushback. Temp triangle. Okay, let's go ahead and remove these guys here. And then we want to do the same thing down here. So we're going to do 10x. There, there, there. I temp triangle. There and there. And then we do indices.pushback. And let's do temp triangle. Okay. So now what I want to do, because I just realized now I have no dependence on I at all. Let's go ahead and get rid of I again, because that was me being an idiot. And let's go ahead and write this. Now let's go ahead and right quit and make that. And let's go ahead and fix everything. So while expected initializer before while. Where are we? We are there. Okay. Now what else do I have? Let's see, 351. Oops. Oh. Well, that's interesting. Probably fixed. Make. Okay, that one's fixed. Unfortunately, we only have one triangle appearing, and it's not even an appropriate triangle, so that says we did something wrong here. Let's see if we can fix that real quick. Here's an article for future reference. Appreciate that. Let me take a look. Good. Figure 1, 2 schemes subdivide a tetrahedron. Yeah, actually this is quite useful. I will, I'll probably look at this today, and we'll go from there. Thanks, I appreciate that. So, what do I want to do? Let me see, triangle.ab, temp triangle indices.pushback. Let me just go ahead and see what we have here. So, for some reason we're only outputting one triangle, when there should definitely be more than that. So let me go here. Let me do 4. Let's say triangle. Auto try. In indices. Let's go ahead and do std cout try.ab. Tab try dot bc tab. Yeah, I was having trouble finding really anything about it, and it was kind of driving me nuts. So try dot ca end line. Let's go here and let's make that. Okay, so it looks like we only have one triangle being created. It is the appropriate triangle, so there is that. But for some reason, we're not generating anything else. CS project merge conflicts. Is CS proj a particular? I don't actually know what CS proj is. CS proj is. I mean, computer science projects, obviously, but I don't know if it's like a specific jargony term. Okay, so while bot count plus plus. So let me just go ahead and also in here do std cout bot count end line. Oop. And now let's go ahead and make that. Looks like we go through all 15, so that's good. The question is why? While bot count is less than triangle number row count. Okay. Oh, you know what I don't do? I just realized at the end here, I also need to do row count plus plus somewhere. So I guess this is gonna have to be down here. I'll do row count plus plus. Now let's go through here and let's make it again. Okay. 1, 2, 3, 3, 4, 5, 3, 4, 5 again, 4, 5, 6, 6, 7, 8, 6, 7, 8 again, 7, 8, 9, 7, 8, 9 again, 8, 9, 10. Let me see, what are we actually looking for? Well, let me see. So this is obviously not the image we want, but we do have 1, 2, 3, 3, 4, 5. Then we should have 4, 5, 6 is another one. Let me see. What are we actually looking for with these triangles? So 1, 2, 3. What's the next one that we have? 3, 4, 5. 3, 4, 5. Oh, that's incorrect. The next one is incorrect. 1, 2, 3, 3, 4, 5. It should be 1, 2, 3, and there should be the end of that. And then the next top count should be 2. And then we should have 4 and 5. Yeah, okay, so it's immediately wrong. Okay. And familiar micro, I missed something. You're picking wrong indices for triangles? Yep, I'm just now noticing. Yep. Okay, so we're gonna say top count. J equals 0, row count plus plus. On the one hand, we are kind of going through everything, so we're getting there. It's just not quite right, so we're gonna say top count is gonna be equal to triangle number of row count minus 1. So row count's equal to 2, so that means that's gonna be equal to, are the corners of the big triangle supposed to be 1, 0, 0? Yeah, there's a lot of things that are wrong. I'm working on that. We have a lot of things that are wrong with the code right now. But yeah, you're right. There's another error there. Okay. So let me see. We have bottom count triangle number row count minus 1, bottom count plus plus. Oh, that would be the issue, wouldn't it? Let me think. Let's remove this bot count plus plus right here. Let's go to, 1 second. Let me go to make. Okay, that's also wrong. 1 second. Okay, let me see here. We needed the bot count plus plus. While bottom count triangle. Okay, so we do a top triangle. Then we do bottom count plus plus. Okay, so this one still doesn't seem to quite be working right. So what I might do, guys, I might end this episode just a little bit early in like 5 minutes. And what I might do is I might finish this one up tomorrow. And then I might also do the recursive solution tomorrow. So I might try to see if I can take some time to finish this up tomorrow and also do the recursive thing tomorrow. I think that's what I might do. Because again, the recursive solution I hadn't considered until Happy Little Rat brought it up. Apparently it's what everyone does, but again, for some reason, I can't ever find this stuff online. Like, I don't know what it is. This stuff is like apparently proprietary. But maybe I just Googled the wrong stuff. So we'll see. Top count. Triangle number row count minus 1. Should be okay. Bottom count plus plus, then row count plus plus. Okay. Well, bottom count is less than triangle number of row count. Let's do less than or equal to, I guess. No, less than's right. Okay. So, what then is the issue? Let's go ahead and run this one more time. And let's run make. Okay, so first triangle's wrong. So 1, 2, 3. Then the next one should be 2, 4, 5. Should be the next one. So we have the 4, 5 right, but the 2 is incorrect. Okay, I'll look that up in just a second. Okay, so what do we have here? Row count -1. Bot count ++. Should be okay. Top count's the one that's wrong here. And then the next one, see 3, 4, 5, and then 3, 4, 5 again. Okay, let me think here. So we have bottom count. Let me see, triangle number, row count -1. That should be 2. Oh, shoot. That's not right. Row count of triangle number, that's going to be 1 for the top count. Shoot, I just realized something. This is actually going to be +1 here. So let me think then. It should start at 1. Let me see, and bottom count should start at 2. So let's go ahead and start row count off at 1. And let's go here to make. Okay, let's see. 4, 4, 5 is clearly not right for the first one. I don't know how we got to 4, 4, 5. Let me see here. Let me go back to 2. Let's go to make. 2, 2, 3 is also clearly wrong. 1 second. Okay, so if row count's equal to 1, then we have 0 plus 1. That should be fine. So we'll have 0 plus 1. So let's set it equal to 1. Yeah, it's definitely a bug in a lot of codes, off by 1 error. So then we'll say bot count is going to equal to 1, but then we're going to increase it by 1, so that should be okay. Okay, so then, what do we say? We say, okay, row count -1. We say while bottom count. What am I outputting? I'm outputting the bottom count. So 1, 3, 6, 10. It should start at, yeah, so it should be 1, 4. Yeah, okay, so that should be right. Let's write this, go here, and let's make it one more time. Okay, so we have 4, 4, 5, 4, 5, 5, 5, 5, 5. Wait, 4, 4, 5. So top count and bottom count are now the same. Is basically what I'm seeing here. So if top count and bottom count are the same, 1, 2, 3, 6, 10. Let's just do this a little bit of a different way. Let's do bottom count ++ down here. Bot count ++. If you get back on the recursive triangle, it's good to take a peek at. Yeah, so I'll take a look at that in just a second. Again, I had not considered a recursive solution, and it seems I don't see how it could be any faster with recursive. So I'm not sure exactly how, but we'll see. All right, I appreciate that. I'll take a look at those links in just a bit. I'll be closing out stream relatively soon. So let's change this to 2, and let's remove the bot count ++ up here. And let's go here and let's make that. Okay, so what is the issue then? The first one is 2, 3, 4, 7, 11, which is correct. 2, 4, 7, 11. 2, 4, 7, 11. That is correct. 2, 4. Oh, 2, 3, 4, 7, 11? Where's the 3 coming from? Well, bot count is less than triangle number of row count. Oh. Oh. This is not going to work. 1, 2, 3, 2, 4, 5, 2, 3. Okay, wait. This is closer than what we were getting before. Let me see. So 1, 2, 3, 2, 4, 5. What's the next one? 2, 3, 5 should be next. 2, 3, 5. Then we have 3, 5, 6. Okay, this actually looks correct. So we have 4, 7, 8. 4, 5, 8. 5, 8, 9. 4, 5, 8, 5, 8, 9. Okay, this is actually correct, but the vertices are not in the right spot. Okay, good. So now we just have to fix where the vertices are, and then we'll be done. Okay, so let me see. What's wrong with the vertices then? I knew the vertices position was actually wrong, by the way. Just throwing that out because these numbers are not correct. Okay. So what are we going to do here? We're going to say, what are we going to say? Num vertex is equal to that. That seems good to me. Vertices.reserve num vertex over 2. Let's actually do reserve num vertex because that's the correct thing to do here. And let's do make. Yeah, I didn't think that would help any. Okay, so we're going to say for I equals 0, I less than number vertex, I plus plus. We're going to say vertex.x Oh, you know what, guys? Let me think. There could be an issue here related to the fact that all of these counts are off by 1. So let me just do this. And let's go make. Okay. Well, we're getting there then. Let me see. 1, 2, 3. 0, 1, 2. 1, 3, 4. Okay, so we got part of a triangle drawn. It's just not quite all the way there. But we're getting there, guys. We're totally getting there. So here's what I'm going to do, guys. I'm going to go ahead and end this here, where we have part of the triangle drawn, and we will finish it up tomorrow. And then we'll take a look at the recursive solution also tomorrow, and we will see what's up and what the difference is there. So now let me go ahead and cd back into the color quantization directory. Let me do a get status dot. And let me just go ahead and add in these files that were changed. So let's do git commit color quantization .pi and color quantization .cpp. Then we're going to add in a message and just say adding final visualization of Octree for color quantization video. Okay. And we're going to do git push origin master so you guys have access to it. Okay. And again, guys, what I'm going to do is take a look at the recursive solution today. Probably during the conference when I should be paying attention to lectures about gauge fields and stuff like that. But honestly, I think we did okay. I will, I'll be looking at the recursive solution today. I'll finish up the solution that we have right now tomorrow, so we'll take the first 30 minutes, probably finishing that up. And then spend the rest of the time working on getting the, getting the recursive solution up. And we'll see what happens. You know, if you guys have any further ideas, CLBI, I'll take a look at what you posted and stuff like that. Obviously, there's a whole bunch of different ways to do this. I just don't do graphics programming nearly at all. I mean, I do GPU computing, but it's a little bit different. So this kind of stuff is completely new to me, and I apologize for that. Anyway, guys, thanks so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where we continue working on this triangle stuff. We made progress today. We're kind of most of the way done. I mean, we finished up the color quantization stuff. That was quite good. We're working on the triangle meshing now. Once that's done, we're most of the way there in a kind of sort of weird way to getting the Galaxy Simulator stuff done. And I'm quite excited with that. Not in next mesh, sadly. Good luck. Anyway, guys, thanks so much for coming in, and I will see you next time. Bye, guys.